Hello. Today we're going to review Chapter 5. And congratulations, by the way. You've made it through another chapter. Assuming you're still with us. Of course, as usual, we're just going to work a bunch of problems from Chapter 5, which was the chapter on the relationships within triangles. In your book, it could have been a different number. That doesn't really matter. It's the same material. And our first problem asks us to identify a triangle by its sides. Remember, our three classifications according to the sides are scaling, where every side is different, isosceles, which has two congruent sides, and equilateral, where all the sides are congruent. They gave us points, so all we have to do is plot these points in our coordinate system. Here's the point O, 0, 0. AA, well, that's arbitrary. You just pick a point where, I could have done it here, anywhere along this line where x equals y would qualify. I just put it here. It's not relevant. What's relevant is that whatever number you pick for A, x, coordinate for Q, has to be double that. So this would be 6, 0. I just chose 3 for A, but it's, as I say, it doesn't matter. We could have put it up here, down here. We'll get the same result. Maybe we should connect these to form a triangle and see how it looks. Well, if we connect it up, it certainly looks like an isosceles triangle to me. But they ask us to justify our answer, and I don't think saying it looks like an isosceles triangle to me would be a considerate, pardon me. I don't think that would be considered a legitimate answer. But all we have to do, we can use our distance formula and easily show that these two are the same length. And computing distances using the distance formula is usually involves long, boring calculations. But in this case, it might not be so bad, because all we have to do is show that OP and PQ have the same length. We don't have to actually compute what that length might be. So, let's give it a shot here. What would the length from here, from O to P, actually be? Let's see, I can do it down here. The change in the x-coordinates, well, that's 0 minus A. We square that. Change in the y-coordinates, well, that's 0 minus A also. So, A squared, we get the square root of 2A squared. Wow, that's a bad 2. Which, of course, is, I said we don't have to actually compute the distance, but in this case it's so easy. Let's just write it as the square root of 2 times A. Okay, that's this distance here. What about this one here? How's that going to work? Now let's use P again, and we've got, or pardon me, yeah, well, not again, let's just use P, period. We'll treat that one like P2, so we'll have A minus 2A for our change in x-coordinate. And A minus 0 for the change in the y-coordinates. And this is going to look just like A squared plus A squared. I don't suppose you'd be willing to take my word for it. That's a 2 there. Okay, there. Looks more like a 2. But that's still just going to be the square root of 2 times A. Same as up here. 2A squared. So, we know that the distances, these two are congruent. That makes them isosceles. How do we know it's not equilateral? check the length of this. Well, that's pretty quick and easy. The y coordinates don't change, but the x coordinate goes from 0 to 6. 6, under special cases, might be the square root of 2a, but I don't think we can do that any way we do it. I mean, any way we try to make this work. For instance, we put a down here as 1. This still has to be 2a. And no matter how we do this, this length here is going to be double. We can have a 2a out here and an a up here. I don't see any way that we could choose our a such that this line down here is going to be equal to this, unless no, I don't see it. We could move a over here, but then this says that a has to be the same for the x and the y coordinate, which means if we choose x to be 0, then y is 0, and we're just right back here where we started. So that it has to be off 0 and along this line somewhere. And then wherever we stop, our q is going to be double that. So there's no way we can ever make this line congruent to these two. So it is isosceles, and no matter how we choose a, it will be isosceles. And no, it's not a right triangle. I mean, it's so obvious from the way we've drawn it, and because of the points. For instance, I'm probably wrong now that I look at it. Gee whiz. Fire this dummy. This one here might actually be a right angle. We need to check that, don't we? Well, okay, let's check it. How do we do that? Well, we find the slope of this line. We find the slope of this line. If they form a right angle, then the two slopes will be negative reciprocals of each other. So let's find the slope of PQ. Let's do that up here. It'll be pretty quick and easy. Remember, the slope is rise over run. So in this case, that'll be 0 minus a. I'm sorry, we're going this way. So we'll start with this one first. And that'll be a, let's start with a minus 2a for the change in x. And of course goes on the bottom. And a minus 0. And that has a slope. Looks like minus 1 to me. We get a, we get minus a, and that's minus 1. And I can tell from looking at this has to have a slope of 1. And maybe you can too. Anything on this line here that meets the vertices of these squares just runs diagonally across like that. That's where x equals y, x equals y, x equals y all the way up. That always has a slope of 1. But we can double check it just to prove that I'm not hallucinating here. We can start with this and go a minus 0. That's the change in the rise, and over a minus 0. And that equals 1. So, in fact, this is a right triangle. There's the right angle. It's an isosceles right triangle. Well, that was fun and probably too long. And as usual, you probably know these reviews take a lot longer than the standard videos. Okay, in this one, they're referring to a traffic triangle. I'm not sure what a traffic triangle is, to tell you the truth. I guess they mean these are footpaths or roads, and the triangle formed by the interior where they meet is called a traffic triangle. I've done a lot of driving. I've just never heard the expression. Sorry. Now, what they've done is inscribed another triangle in here. They're calling this the middle triangle. How did they go about inscribing this? Well, from the way they've drawn these hash marks, it's kind of obvious. This is a midpoint of this segment, and this is the midpoint of this segment. So we connect the two midpoints, and we have what we learned is called a mid-segment. We do the same thing here and here. So we've connected all the mid-segments. We also learned that our mid-segment is half the length of the side it is parallel to. Hope that didn't sound confusing. All that means is, for instance, this mid-segment here is half of this. This mid-segment here is half of this side, and this mid-segment is half of this side. Luckily, they didn't ask us what the lengths of the sides are, because unless they gave us more information, there's no way we could figure that out. But we know the sum, the middle triangle, is 10 feet. If we had this and this and this is 10. Well, if we double each of these, if this is A, this is B, and this is C, I'll just do it. The sides of each of these are, let's say, A, B, and C. And let's say A represents the length of this, B represents the length of this, and C represents this length. Well, this side over here has to be 2C. This side over here is 2A, and on down the line. So the perimeter of the large triangle, we'll say P sub L, is 2A plus 2B plus 2C, and of course we can easily use our distributive property to rewrite it this way. Now, A plus B plus C, that's the perimeter of the inner triangle, which we know is 10 feet. So what we get is 20 for the perimeter of the large triangle. And here's one where we don't really have to come up with exact numbers. We just have to make comparisons. We have to decide if something's larger or smaller than something else. It's usually a bit easier, but not always. We'll see. What they have here is a wooden step ladder. The support, I'm referring to this little cross piece here, it's parallel to the floor. That's important. That means that it's parallel to this line right here, which is 16 inches. They also tell you that it is 5 inches above where the mid-segment of the triangle would be. In other words, we've got a midpoint for this and a midpoint for this, and if we draw our mid-segment connecting our two midpoints, this is 5 inches above it. Now, with this one, once again, we're forced to eyeball something as opposed to actually prove it. But we could do this and be fairly sure we're right, I guess. They ask if this support up here, the one that is 5 inches above the mid-segment, if that's more than, less than, or equal to 8 inches. Well, we already know that we connect the two midpoints, create a mid-segment, and that mid-segment is 1/2 of the side that it is parallel to. This is 16 inches, so if we were to connect this, create a piece here and connect the two midpoints, we would have an 8-inch cross piece. Now we've moved up, as you see these two sides are coming together at a vertex right here. That's what makes it an angle. If they didn't come together, that wouldn't form an angle, they'd be parallel. As we're moving towards the vertex, the lines get closer and closer together, which means this piece right here the distance from this line to this line must be shorter. And remember, we have the distance from a point to a line is the perpendicular distance. We haven't even defined the distance from a line to a line, but we can easily define the length of a piece, which goes from some point on the line to some other point on the line. And in this case, they told us it was parallel. That makes a big difference. If this thing wasn't parallel, we couldn't know by the fact that it's above this mid-segment that it's smaller. I mean, we could have started here and then drawn our line way up there. That's probably going to be longer than this crosspiece. It has to be parallel. In a sense, one way you could look at it is like this. When you put this mid-segment in here, we've created a whole nother triangle. And this mid-segment has an 8-inch. It's 8 inches long. If we put in a mid-segment in the appropriate spot, that will be 4 inches. Well, our crosspiece has to be somewhere between the 8 inches and the 4 inches, which is less than 8 inches. So, if you're wondering, the correct answer is less than 8 inches. And you probably could have spotted that in like half a second by recognizing that the mid-segment would be 8 inches. This is above the mid-segment. It's towards the vertex. So it must be smaller. Well, less than 8 inches. Yeah, here's one. It's kind of like find the error problem. We've got instructions for making a triangular earring out of a piece of silver wire. It's gotta be the most boring earring I ever heard of. Sounds like you're just hanging a coat hanger off your ear. Well, a small version of a coat hanger. Doesn't sound all that great to me. But let's check it out. Who knows? There may be somebody somewhere who would really like to have a triangular earring made from silver wire. Could we do it this way? One side is 3/4 of an inch, another side is 5/8 of an inch, and another side is 1.5 inches. Well, first, I think what we're going to have to do is apply our triangle inequality and see if it's possible for these measurements to add up to a triangle. Remember, we have to have that the sum of these two is greater than this, the sum of these two is greater than this, and the sum of these two is greater than this. Well, this is our smallest side, and it will be greater. Okay, how about if we take this and see if it's greater than this one? Probably the first thing we should do is put everything into a common denominator. Makes life easier. So we could write 6 over 8 for one side, 5 over 8, and what's that, 12 over 8? I think so. Now, we find two of these that don't add up to one of the other ones. In other words, since they all have a common denominator, we can just look at these upper numbers here. And 5 and 12, 17, oh, that's bigger than 6. Okay, 6 and 12 is 18, that's bigger than 5. Okay, 6 and 5 is 11, and that's, oops, that's not bigger than 12. We have a problem. The sum of these two sides is not greater than this. And remember, for any triangle, pick any two sides. Doesn't matter which two sides you pick. Add them up, you got to get a number. Add up the lengths of any two sides. And you'll have to get a number greater than the length of the remaining side. And when we add these two up, that doesn't happen. We get 11 over 8, which is not greater than 12 over 8. So, we're out of business. And the poor woman's not going to get her triangular silver earrings. Bummer. Yeah, here they're getting maybe a little bit tricky. What they're doing here is giving us one side of a triangle and the coordinates. So maybe I should write those in. A is at 0, 6. That's right here. Now B, that's over here, minus 2, 4. And the centroid, that's where the medians intersect. That's right here. And that's at the point minus 1, 2. That's that point right there. So, what do we know about the point where the medians intersect? Well, that's what the centroid is. What's the median? Remember, that's the point that goes from vertex to the midpoint of the opposite side. Now I redrew a triangle with the medians over here, just to remind you what they are. It goes from the vertex to the midpoint, which didn't draw that very well, but this is the midpoint of this segment. This is the midpoint of this segment. Vertex to midpoint. That's a median, and where the medians intersect is called the centroid. That's this here. And remember, we have an important fact about these medians and the point where they intersect, and that is that this side is 1/3 of the whole, and this is 2/3 of it. In other words, it breaks it up into thirds. So if I label these, this line I drew in here, this represents a median from this vertex to the midpoint of a side that we haven't figured out yet. We don't know what the orientation or the length of this side is, but we do know it has to cross this median. Same thing over here. I just went ahead and drew them in. And here's the one that's really important that we're going to use to figure out where C is. C goes, this median goes from C, the vertex, to the midpoint of AB. So all we have to do to get started is figure out what is D. We find the midpoint. Once we find that, we can figure out what our line is, because we've got a point here, and then we've got point P is already given to us. We can draw a line through those two, which extends to C. At that point, we know that C lies along this line somewhere, but we don't exactly know where. All we have to do is compute the length of this, and this part will be double, and then we can find this. In other words, the part from P to C is 2/3 of the part from D, the whole thing from D to C. Sounds more complicated than it is. Let's get D first. That's the midpoint. And how do we find midpoints? Well, we just take the average of the x-coordinates and the average of the y-coordinates. So we've got 0 plus a minus 2 over 2, comma, six plus 4 over 2. And that should give us the point minus 1, 5. Just barely squeeze that in at the end there. And what do we have here? Minus 1 and 5. So it should have been just up here just a little bit. But we got the x-coordinate right. That's cool. Why is that cool? Because eventually we're going to have to figure out If this is 1/3 of the length, then we got to go 2/3. In other words, twice this in the same direction. Well, we got a vertical line, so that makes it real easy. In fact, you can just count this. This is a y-coordinate of 2. This is a y-coordinate of 5. Let me go ahead and draw it in there. -1, 5. So the length from here to here is 3. Well, we just double that. We go down here 6, and then we have our proportions correct. This is 2, then we should go all the way to -4. And what do we have? We have -1, -4 as the coordinates for C. Remember, how do we do that? First, we find the midpoint. They gave us the centroid, and we know that the distance from the midpoint to the centroid is 1/3 of the total, which means from the midpoint to the vertex is 2/3. If this part is 1/3, all we have to do is double it, and that's the distance from here to here. And that's exactly what we did. We found this distance to be 3, we doubled it. The distance from here to here was 6, we go 6 units down, and boom, there we are. If this didn't turn out to be a vertical line, we'd have to do a little more work, because our distance formula would be a little more complicated. But they gave us a break. This vertical line makes it fairly easy to compute where C is. And if we want to, we can now draw on the triangle. Now that we know where C is, I think we can probably do it. It's a little crowded, but you might be able to see what's going on here. Those medians that I drew in without having the sides, I just drew them from the vertex to the centroid, and they had to extend out. They came kind of close, especially on this side. This looks like a midpoint here. This, well, I don't know. It doesn't look like I drew it very well. I think maybe I should have. I'm not sure what I should have done. I should have drawn it better is what I should have done. So I think the midpoint's probably just over here a little bit. And these two weren't really that important. But from the information given, we know that these two would have to intersect here, because that's the definition of the centroid. And that was the important thing to remember. The definition of the centroid, and the definition of the centroid is the point where all the medians intersect. Of course, you had to remember what a median was. That's from the vertex to the midpoint of the opposite side. And then you had to remember the fact that the centroid breaks your median up into sections of 1/3 and 2/3. So, remember a few important facts, and you got the whole thing real easy, I guess. Well, for this one, we had to remember another one of those boring facts. And this one is the point of intersection of the perpendicular bisectors is equidistant from each point of the triangle. Remember, that's also called the in-center, because that's the point where you could center a circle that would pass through each point in the triangle. Well, what we have here, they drew these little hash marks to show you this is an angle bisector. The angle bisectors don't produce a point which is equidistant from each point in the triangle. Your angle bisectors produce a point which is equidistant from the sides of the triangle. That's not what we want. So we want the perpendicular bisectors. These are the ones which bisect the sides. And I think I've mentioned before that in reality, if you get everything right, you only have to draw 2 of them in and see where they intersect. Or compute an equation for 2 of them if you have a coordinate system that you have coordinates for each of these vertices. Then you can compute the midpoint, and you can compute the equation of a perpendicular line. You can do the same thing over here, set those 2 equations equal, and they will intersect right here. In this case, I think they just wanted you to eyeball it. And in fact, they already drew them in for you. Theoretically, if we draw our third perpendicular bisector, it'll go right here like this. Because all three of them have to intersect at the same point. So if we get everything right, we only have to draw in two. And that's what they did. Here's a perpendicular bisector. There's a perpendicular bisector. The point where they intersect is equidistant. We could draw a circle with this thing centered. I don't think I said that right. We could draw a circle with B as the center, and it would pass through each of these points. Maybe we can do it. Let's see. When I said, let's see if we can do it, well, theoretically there is a circle which passes through these points and is centered at B. That's always true. Whether I can actually draw that circle or not, that's the part. That's what I meant when I said, let's see if we can do it. The circle definitely exists. Whether I can create that circle or not, well, that's a whole separate question. This circle here should be centered at B, and it passes through each of these points. Looks about right to me. So that's all you had to do for this one, really. It just hinged on recognizing that the point that is equidistant from all the vertices of a triangle is the point where the perpendicular bisectors intersect. Not the angle bisectors, the perpendicular bisectors. It's almost the reverse of what you're doing here. You're taking the distance, you're bisecting a side, in other words, and you're finding a point that is equidistant from the vertices. Here you bisect the angles, and you find a point that is equidistant from the sides. So in one case, you use your sides as a reference, and you find a spot equidistant from the points. In the other case, you use the angles for a reference, and find a spot equidistant from the sides. It just goes back and forth. So if you're going from the midpoint of the sides, you're finding a spot equidistant from the points. You go from the midpoint of the vertices, you're finding a spot that is equidistant from the sides. You kind of reverse things, if you see what I mean. At least that's the way I remember it. You may have a better way. Your instructor may easily have a better way of beating this into your head. But you do need to remember it, unfortunately. It's not the most exciting fact in the world, but you're going to have to know it for the standardized exams. Well, here's one you can probably look at and get the right answer. At least you would pick the right path. But the answer says explain your reasoning. And if you just guessed, you'd probably get the explanation wrong. Unless your instructor is willing to accept I just guessed as a legitimate explanation. I don't think most of them will. So how the heck do we figure out which one is shorter? We've got no coordinates. We have no way to actually compute any distances. But we have a couple of angles here, and we're looking for shortest distances. Sounds like a job for the hinge theorem to me. That's the one that says the side opposite the biggest angle has to be the biggest side, and the side opposite the smallest angle has to be the smallest side. So let's take a look at what we got here. These are the two paths. Now, these are the sides, if you want to call them that we're concerned with. So what we're concerned with really is this angle and this angle. Now, this angle and this angle would be supplementary because this is a straight line. So this angle right here is 180 minus 44. And this one up here, the same reasoning, is 180 minus 62. without even doing any arithmetic, what do you think is smaller? 180 minus 44 or 180 minus 62? Well, I'd say this is the smallest one. That means this here is the smallest angle. So this must be the smaller side. This angle. Keep in mind that they share this common side. I mean, if you just take two completely disjoint triangles and say that the angle opposite one side is larger than the angle opposite the other side in some other triangle, therefore that side must be larger. That's nonsense, because you don't know anything about the relative overall size of the triangle. But here we have two sides that are congruent, if we consider these as triangles, and that helps. Because that was part of the hinge theorem. The hinge theorem says that to apply it to two separate triangles, remember, within one triangle, no problem, you can always apply the hinge theorem. But when you've got two separate triangles and want to apply the hinge theorem, you have to know that two of the sides are congruent. Then you can determine that the largest third side is the one opposite whichever angle is larger. And they gave us that these two sides are congruent. This one is congruent to itself. So we do have conditions met for the hinge theorem. What I'm getting at is down here. This angle, take my word for it, is bigger than this angle here. Not much, but a little bit bigger. Does that mean that this side is larger than this side? Well, no. And the reason is that this side is not congruent to this side, and this side's not congruent to this side. We have to have two of the sides congruent before we can start using our hinge theorem. If we don't have that, then it doesn't mean anything, because even though this angle is larger, this is just a way bigger triangle. If you have two sides that are congruent, then you don't have a situation where you have what you would call a much larger triangle, so that the side opposite a smaller angle would still be larger because it's a bigger triangle. No. As long as you have two sides that are congruent, you don't have this situation that I just drew down here. And that is a key to using the hinge theorem, when applying the hinge theorem to two different triangles. Well, there's an interesting problem because it's general, but they would like us to use an example. Okay. Examples are usually easier than flat-out proofs or even demonstrations. So how would the area compare here? Well, it's an interesting idea. I think there's a couple ways to show what's going to happen. We can use our straight area formula. That might work. For instance, we know that this here is 1/2 of this side, the side parallel. This is 1/2 of this. Since we're going to use a specific example, it says right here, use an example, why not use an equilateral triangle? That doesn't prove that it's true for all triangles. On the other hand, they didn't ask for a proof. They said give us an example and relate the area, giving us the impression that if we can find out what's true for a particular triangle, it'll be true for all triangles. So what the heck? Let's try an equilateral triangle. What does that mean? Well, as I said, this is half of this long one, this is half of this long one, and so forth, which means if this has side A, then this has side A, and this is length A. An equilateral triangle. That means this one is A over 2, This one is a over 2, and this side is a over 2. What about these triangles that are formed here? Well, this is a, but this is by definition a midpoint. So this side is a over 2. This side is a over 2, and we can do that same reasoning all the way around, which means we have now broken this up into 4 equilateral triangles. We've got this one right here in the middle, plus these 3. Well, this one is, we've got 4 equilateral triangles, all exactly the same. The base and height, this is the height and this is the base of this triangle, has to be the same as this. They're all congruent. They all have side a over 2. They're all equilateral triangles. And there are 4 of them that are congruent to each other. And those 4 make up the total area of the large triangle with side A. On the other hand, the inner triangle makes up one of those 4. So I would say it's 1/4. This is 1/4 the area of the total. Easy to show with equilateral triangles. In general, if it wasn't an equilateral triangle, it's fairly easy to see that we're going to cut the base in half. Cutting the height in half that would be the altitude, is a little less obvious, but that is in fact what happens. So what happens is that you get the area turns out to be 1/2 of what? Well, the base is 1/2 of the original base, and the height is going to be 1/2 of the original height. And what does that give us? Well, 1/2 BH, the standard formula, times 1/2 times 1/2, which is 1/4. I like the visual way myself. It just very graphically shows that this inner triangle is going to be 1/4 of this. And it turns out it doesn't matter whether it's equilateral or not. But they didn't ask us to prove that. They just said, come up with what you think is going to be a relationship between the large one and the inner one, and use an example. And that's what we did. So I would give myself full credit for the graphical answer. I don't know what your instructor might do. They might be looking for a more algebraic way to do it. But as I think I've mentioned 500 times before, there's more than one way to solve a math problem. Well, here's one that involves an isosceles triangle. We're going to use an 18-inch wire to form an isosceles triangle, which means the perimeter is 18 inches. If we have an isosceles triangle, this is the vertex angle. These are the 2 base angles. We know that these 2 sides are congruent because it's an isosceles triangle. We know that these base angles are congruent because it's an isosceles triangle. We know that they add up to 180 because it's any kind of triangle. If this is greater than 60, each one of these must be half of 180 minus 60 because that's what's left over. In other words, we take 180 and minus 60, and that's 120. Which means that these would each be 60 degrees also. But this angle here is greater than 60 degrees, which means that if this was 60, these would also be 60. That means they have to be, each of these angles here is less than 60 degrees. Less than 60 degrees. Is that important? Well, what it tells us is that this is the largest side. After all, an isosceles triangle can have legs which are both longer than the base. This is called the base. Or the legs could be shorter than the base. if this is x, and this would be x, this is something greater than 2x. Don't know what it is, we just know it's this side here is, pardon me, that's not right. My mouth's not connected to my brain this morning. This side here is greater than x. That's all we know. It's larger than either one of these. It couldn't possibly be larger than the two of them together. That would violate the triangle inequality. So it's greater than x, and it's also less than 2x. So if we call this side b for base, I can put it in here. It's greater than 2x, and it's less than x. Now I can rewrite these two conditions over here. B is between 2x and x. And they're asking us to describe possible lengths, which I take to mean an interval, which would be legitimate for this. Well, these two the perimeter altogether would be x plus x something between x and 2x. And let's write that out and see what kind of sense it makes. And so what do we have? We have the perimeter is equal to x plus x, that's these two sides, plus, we know this is bigger than x, so we'll say x plus some little number that we don't know what it is yet. That makes this, and this number here is positive. That means x plus this. And let's call it delta, just because that's what it is. So, what we have here is that equals 3x. Now, let's forget the delta for a minute, and suppose all the sides were equal, and that equaled 18. Okay? Then we would have that x equals 6. However, this would, we do it this way if all the sides were equal, but they're not. So x must be less than 6, and this is greater than 6. So, over here, we can write that b, it's definitely greater than 6. On the other hand, it is less than these two. So let's see if we understand what we've got so far. If all the sides were equal, they'd be 6 apiece. But they can't be equal. These two are congruent, but this one is bigger. That means these have to be less than 6. This has to be greater than 6. But it has to be less than 2 of them together, which at most would be 12. But it has to be less than that. So b is between 12 and 6 here. I wonder if we can do anything more. But actually, I think we can do a little better. B has to be greater than 6. We know that because of the size of the angle here. However, does that mean just less than 12 is going to work? Suppose B was 11. Well, the whole thing is 18, so that means we would have 7 inches left to divide up between these two sides. That would be 3.5 inches each. So if this were 11, these would each be 3.5. Oh, wait a minute. 3.5 plus 3.5 is 7. That's not greater than 11. The sum of these two sides has to be greater than this. This has to be greater than either one of these, but the sum of these has to be greater than this. So 11 doesn't, it has to be less than 11, so we can put that here. Okay. What about 10? Does 10 work? Well, that means the sum of what's left over is 8, but 8 is less than 10. So it definitely has to be less than 10. What else? Suppose we use 9. Well, that leaves, perimeter was 18. That leaves 9. Well, okay. That means if this is 9, then the sum of these two is 9. But the sum of these two has to be greater. So 9 won't work. But anything less than 9 would. For instance, if we drop down to 8, then we've got 10 left over, and 10 is greater than 8. The way we can decide where to cut this off is to just subtract b from 18. If the number we get is smaller than b, we're out of luck. If it's equal to b, we're still out of luck. If it's greater than b, now we've got something. Because what's left over would be the sum of these two. And the sum of these two has to be greater than b. So that's how you can figure out your other limit. What can you subtract from 18 that will leave you a number larger than what you subtracted? And that would be anything less than 18 divided by 2. When you subtract 18 divided by 2 from 18, you get 18 divided by 2 left over. So you're right on the edge of the triangle inequality. But remember, there is no triangle equality. You can't set these two sides equal to this side. If you do that, you don't have a triangle, you have a straight line. The triangle inequality means that the sum of these has to be greater than this. So 18 over 2 is the cutoff. In fact, b has to be smaller than that. So if we put it here, boom, 9 and 6. Now you have an interval that actually works. For instance, stick in 8, and you've got 10 left over. That works. 5 here, 5 here, 8 here. Makes sense. That'll work. So this problem was so long you probably forgot what we were doing back at the beginning. Remember, we used the hinge theorem. The fact that this was greater than 60 degrees, meaning it's larger than either one of these two. Why was that? Because these two have to be congruent. Why? Because this is an isosceles triangle. So these two sides are congruent. The fact that this is isosceles is a huge part of working the problem and what you know about isosceles triangles. These two angles are going to be congruent, so they will have to be less than 60 because this one is greater than 60. Subtract that from 180, you get 120 left over, you divide by 2, you get 60. So if this is greater than 60, these will have to be less than 60, or they're not going to add up to 180. On the other hand, since this angle is larger, this must be the largest side. So we know that this side is larger than either one of these. On the other hand, the triangle inequality tells us that these two together must add up to more than this. So it's greater than 6. Not the fact that they can't all be equal. I think that was, we know they can't all be equal because this angle is larger. If they can't all be equal. This is the largest one. These two add up to more than this. On the other hand, this by itself is more than either one of these by themselves. And that leads us to an interval between 9 and 6 that'll work for b. It has to be greater than 6, because that's what we got when we set them all equal. And it has to be less than 9, because that's where the triangle inequality leads us. I hope you got all that. Okay, this is one where really all you have to do is remember what a circumcenter is, and then our little facts about circumcenter. Remember, a circumcenter is the point where the perpendicular bisectors, I think they're perpendicular bisectors. Yeah, it's the point where the perpendicular bisectors intersect. Remember, the incenter, that's where the angle bisectors intersect. I hope I didn't refer to it incorrectly in a previous problem. It's not impossible. The circumcenter, that's where the perpendicular bisectors intersect. It's equidistant from the vertices of the triangle. The incenter, that's where the angle bisectors intersect, and that point is equidistant from the sides of the triangle. What we want is the circumcenter. And for an acute triangle, the circumcenter is inside the triangle. For a right triangle, it lies right on the hypotenuse. And for an obtuse triangle, it lies outside, if that's one. Is that one of the answers here? Yeah, there it is. So if you forgot, you could draw yourself a triangle real quick. Draw in the perpendicular bisectors and notice that the circumcenter is outside the triangle. Or you can just remember that for acute triangles, it's on the inside. Right triangles, it's right on the triangle on the hypotenuse. And for obtuse, it's outside. And here's another one which hinges on the hinge theorem. Why can we use the hinge theorem? We have two congruent sides. This is congruent to this, and this of course is congruent to itself, which means we can compare sides opposite corresponding angles. And these are the corresponding angles now, because this congruent side corresponds to this congruent side, or let's say this side corresponds to this one. So we have an angle in between two congruent sides, here and here. This angle is bigger than this one. So this side here must be bigger than this side here. Or conversely, this side is less than this side, or x is less than h. Pretty easy. Again, just spot your hinge theorem. And remember, we can apply it because we have an angle included between two congruent sides. That's the important part here. This is always congruent to itself, and we know that these two are congruent. That's why we can apply the hinge theorem. This one's pretty easy. We just have to think back to some of the stuff we learned in previous chapters, like congruence. We have that this side is congruent to this side. They tell us that. And this side, of course, is congruent to itself. If this is a right angle, then this here must be a right angle also. There's more than one way we can prove that, and we've already done it. This is a straight angle. This is 90 degrees. This one must be 90 degrees because they have to add up to 180. That's the simplest way to look at it. So we could say we had side angle side, which causes it to be congruent. Or we could use one of our, well, we don't have a hypotenuse leg because we don't know that the hypotenuse is hypotenuse. I still haven't figured out how you're supposed to say that. Maybe you're supposed to say there's an hypotenuse and look, there's another one. Just never even try to pluralize it. We don't know that they're congruent, but we do have that the legs are congruent, and of course the angle in between is because they're both right angles. So by side angle side, we know that these two triangles are congruent. Once you know that, you're pretty much done. Want to know the perimeter of RST? Well, that's just, now all we can do is put in some numbers. And this, of course, this is congruent to this, this is congruent to this, and this, well, we don't care what that is, because the perimeter they want is RST, this whole one here. So, once we have congruence, we just add it all up. 2 times 6.8 is 13.6, 2 times 8.5 is 17, and the whole perimeter is 30.6. Fairly easy, just had to spot the congruence. They're telling us that n is the in-center. What does that mean? That means that it's the same distance from each side of the triangle. In fact, they drew in those distances right here. Remember, it's the perpendicular distance from the point to the line. That's Fn. Well, these are all the same distance. So if we find any one of these, Fn, Gn, or En, we're done. Well, suppose we found this one. We're given measurements for this. We don't even have to worry about whether this triangle is congruent or any of that, because we already know that each of these is congruent. We're also given 2 dimensions. We've got the hypotenuse here and the leg for this right triangle. We know it's a right triangle because they gave us this little right angle symbol here. So now we can apply Pythagoras' theorem, which we haven't used a lot of so far in this class, but this is the, I think Pythagoras' theorem would be the simplest way to solve this. And that says that the hypotenuse squared is equal to the sum of the squares of the 2 legs. Well, one of the legs is 12. The other one we don't know. So I'm just going to call it x. So 12 squared plus x squared is 13 squared. We do a little rearranging, pardon me, and we get 13 squared minus 12 squared equals x squared, or x equals the square root of that. Well, 13 squared is 169, right? 12 squared is 144, and we need the square root of that. And I think that turns out to be 25, which equals 5. So the length of NG is 5. But these are all congruent, so this one is 5 also. In fact, they didn't ask, but this one would be 5 as well. That's all you had to do. First, just spot that finding any one of these will solve the problem, and then use Pythagoras' theorem to find this one. Now here's one where they give us some measurements, but no actual coordinates. I think these measurements are going to turn out to be a little bit irrelevant, because what we're going to do to find a spot that's equidistant from each side, remember, we bisect the angles, we find a point equidistant from the sides. So if we draw in our angle bisectors, the point where they all intersect will be equidistant from each side of the triangle. So, see, there's one, there's another one, and there's the third one. So we've got these angle bisectors. That is the point equidistant from each side. What theorem did you use? Well, back a ways we had a theorem called the that's called the concurrency of angle bisectors theorem. I probably just call it the angle bisectors theorem, but maybe you should be more precise on the test. Concurrency of angle bisectors theorem would be the theorem, and how you did it was to draw in the angle bisectors. Not really a lot of not any numbers at all involved in this. It's really just a just testing you on methodology, I guess you could say. You don't actually have to compute anything. Just draw the angle bisectors, find your point, and then cite the theorem, which, as we say, is the angle bisector theorem. Yeah, there's one with quite a few steps, but doesn't look like it's really all that hard. Then again, I could be wrong. Let's see what's going on here. First thing we probably ought to do is identify the points they're talking about here. 8 minus 1. Let's see, there's 8, there's minus 1, so there we go, that's 8 minus 1, and that's point A. What about B? 6, 3. Alright. And that's point B. Now, if we connect them, now we have a line segment, and number 1, what's the midpoint of AB? And the slope. Wow, they want both of them. Well, okay. Midpoint. Well, the x-coordinate of the midpoint would be 6 plus 8 over 2. Midpoint of the y-coordinate would be 3 plus or minus 1 over 2. And what does this turn out to be? 14 over 2, 7, and 1. So that's right there. And looks about right to me. What about the slope? A little bit different. Let's take 3 minus a minus 1. Remember, rise over run. 3 minus a minus 1 over 6 minus 8. So that's 4, and that's minus 2. We have a slope of minus 2. Okay, pretty easy so far, right? Rise over run, average of the x-coordinate, average of the y-coordinates. Now, what other outrageous questions are they going to ask us about this here line segment? Use what you know about slopes of perpendicular lines to find the slope of the perpendicular bisector. That would be the one that goes like this. And intersects at a right angle. Well, remember the slope of the perpendicular line is the negative reciprocal. So this would be reciprocal is 1 over minus 2. The negative of that would just be 1 over 2. So we should get 1/2. So the slope is 1/2. But now they want to do something harder. They want the equation of the line. So let's put our line. Gee, we're going to need more room here. Is mx plus b. In other words, our slope-intercept, because we already have the slope. So right off the bat we can write 1/2 x plus b equals y. Well, now all we have to do is find some point on this line, plug in the x and the y, and solve for b. Now what do we have for a point on the line? How about our midpoint? That was over here, 7, 1. So if I put in 7 for x here and 1 here, then I'll get that b equals 1 minus 7 over 2. That's minus 2.5, isn't it? You can check that. 7 over 2 is 3.5. 1 minus 3.5 is minus 2.5. So, works for me. So, the equation here should be 1/2 x minus 2.5, 2.5. May have written, what, 11 over 5 maybe? I need to go back to school. How about 5 over 2? Now, this could have been 5 over, I don't know where I got 11 over 5. Please forget I ever said that. It doesn't make any sense at all. 5 over 2 would work here, or 2.5. Or any other fraction that works out to 5 over 2. I guess 10 over 4 would work, like I said. I don't know where 11 over anything would have come into that. It doesn't. I shouldn't have said it. We have one part left. We found the midpoint. That was 7, 1. We found the slope. That was minus 2. We found the slope of the perpendicular. That was 1/2. We found the equation of the line. That's 1/2 x minus 2.5. What's left? Now we have to find a point D. Okay, took me a second to figure out what they were asking for here. Just find any old point that is on the line that we just found. In other words, any point that satisfies this here. How about the point where y equals 0? That means this whole thing has to be equal to 2.5 or 5 over 2. So x would be 5. So the point 5, 0 would lie on this line. So I didn't draw the perpendicular perfectly. In fact, not very well at all. I would have had it coming down here at 6, and that's not right. The actual intersection of this perpendicular with the x-axis would be 5, 0. That's a point on the line. And now, if we connect these, that's what they're saying here is connect these here. What do you notice? Well, every point on this line is equidistant from these 2 points, which means this point must be equidistant from this point and this point, or this side and this side. We've created a triangle here, so these 2 segments or sides of the triangle, they're congruent. How do you know that? I think that's probably our perpendicular bisector theorem, but let's check. Well, we already know from the perpendicular bisector theorem that these 2 distances have to be equal. But they say find them, so I guess we should, since they asked us to do it. Okay, boss, we'll find the distances. So what do we got here? Distance from here to here. Remember, it's the change in x squared plus the change in y squared, and then the square root of that, just our distance formula. So we'll take this as P1, I guess. Doesn't really matter. So we'll have 6 minus 5 squared plus 0 minus 3 squared, and we're going to take the square root of that. Well, this is 1 squared, which is 1, minus 3 squared, which is 9, 9 and 1 is 10, so we get the square root of 10 here. What about these 2? Well, let's try it down here. Remember, this is our equation for the line that goes right here. Yeah, we can use that for P1 again if we want to, and take 5 minus 8. Quantity squared. Plus 0 minus 1. Five minus 8 is 3. Squared is 9. 0 minus a minus 1 is 1 squared. No, we just have 9 plus 1 again. And of course we need to take the square root of that. So this is the square root of 10. Now, we really didn't need to do this to verify that these two are congruent. I guess they just wanted you to use the distance formula just to prove you knew how to do it. Because we already know from the perpendicular bisector theorem that you can pick any point on this line and it's going to be equidistant from the two endpoints of the segment which you just bisected. That stems from the fact that, well, it stems from the fact that it's perpendicular bisector. This is the midpoint and this line is perpendicular. If this line wasn't perpendicular, that wouldn't work. If we drew some other line through the midsegment, then no, we wouldn't have that. But the perpendicular bisector has that unique property that every point on this line is equidistant from the two endpoints of the segment. So it really wasn't necessary to find the actual length of these two to know that. But it doesn't hurt to review your distance equation. Now we're going to find they've given us the coordinates of the vertices of triangle JKL. Our job, should we choose to accept, is to find the coordinates of the centroid. What's the centroid? That is where the medians intersect. What's a median? That's the line from the midpoint of one side to the opposite vertex. And the midpoint of this side to the opposite vertex. I only drew in two medians because if we didn't make any mistakes, the third one will have to cross at exactly the same point. So how do we find the coordinates of this thing here? First, I think we're going to have to find a midpoint here. And then we're going to have to find a midpoint here. We're going to find equations for these lines, which I'm guessing are going to be kind of easy because they look kind of vertical and horizontal to me. But let's see what the numbers tell us. And I just cut out part of our grid so we have more room to write our equations down here. Now what's the midpoint of this line segment? Well, that's real easy. We want the average of the x-coordinates. That's 4 plus 10 over 2. And then the average of the y-coordinates, which is 8 plus a minus 4 over 2. And what do we get? 7. And 8 plus a minus 4. That's 4 divided by 2 is 2. Now, does that make any sense? Well, let's see here. There's 7, 2. Yeah, it looks like a reasonable point for a midpoint. Well, what about this one here? So maybe we gotta put this in here. We got 7, 2. And what do we call that? Yeah, let's call it A. What about down here? Well, same thing. Average of the x-coordinates is 10 minus 2. Well, 10 plus a minus 2 if you like that better. Over 2. And then we got 2 plus a minus 4. Divided by 2. That will give us our other midpoint, and that's 10 minus 2 is 8 over 2, that's 4. And minus 2 over 2 is minus 1, I think. Yeah. Minus 4 minus 2 over 2 is minus 1. Does that make any sense? Then let's see here. There's 4 and minus 1. Well, that's right about where I drew it. Either I eyeballed it really well, or I computed it wrong. Let's hope I computed it right and I eyeballed it right. We'll pretend two things went right at the same time. And let's put it in here. 4 minus 1. Call that point B. Now remember, why the heck did I do all that? Well, if we've got 2 points, we have an equation for a line. We've got 2 points, we can find the equation for the line. And where those two lines intersect, that will be the centroid. Well, the equation for this line, we can do it quantitatively. What the heck? We've got the rise, which is 2 minus 2, over the run. Now 2 minus 2 is 0. So if we get a 0 up here, it doesn't matter what we put down here. It could be anything, it's still going to be 0. So our slope here is 0. Which means the equation for this line is going to be 0x plus b. Well, y-coordinate here is 2, y-coordinate here is 2. It's a straight line, so b must be 2. So the equation for this line is a very simple y equals 2. Boom. All done. What about this one here? Well, you can immediately spot these coordinates, x-coordinates. The change in the run, that's the bottom part here. Ooh, we got a problem. That's going to be 0. The change in the run, the rise over the run. Now, the rise is 8 minus a minus 1. That's 9. But the run, 4 minus 4, that's 0. Doesn't matter what you put on top of 0. It's undefined. This is vertical. So it's, as an equation, it doesn't really make much sense. It's just the line x equals 4. That's about all you can write. So that's our other equation for the line. So where do the lines y equals 2, that's everything along this line, and x equals 4, which is everything along this line, where would they intersect? Well, I don't think you need any computations for that. 4 comma 2. So that's that one right there. Okay, now we've got that point. I think I need to probably erase all this stuff because we've got a whole bunch more equations to do. And this next part is something we didn't hardly do much of. In fact, we didn't do any of it in this chapter, which involved finding averages of more than 2 numbers. But that's okay because it's one of the things we know how to do. So what would the average of the x-coordinates be? It would be minus 2 plus 4 plus 10 divided by 3. This is 4 minus 2 is 2 plus 10 is 12 divided by 3 equals 4. That's the average of the x-coordinates. What about the y-coordinates? Well, let's see here. That's 2 plus 8 minus 4 divided by 3. You got 8 minus 4 is 4, plus 2 is 6, divided by 3 is 2. So we have x. I'm going to put a bar over it to say that's our average x-coordinate. We don't use that notation much in this class, but I didn't just pull that out of my hat. It's actually common notation for this. This is the average x-coordinate is frequently written as x bar, and the average y-coordinate is frequently written as y bar. Not so much in this class, because we don't really work with averages of the x-coordinates and y-coordinates very often. But what did we get? We got x-coordinate of 4 and a y-coordinate of 2. Oh, son of a gun, look at that. The centroid was also 4, 2. Well, that's interesting, isn't it? The centroid, which I think I've mentioned before, if I didn't, I'll tell you now, is like a center of mass. It's the point where you can balance everything. If you were making mobiles, this is where you would poke the hole in order to balance this thing on the end of a needle, or on the top of a needle, I guess it would be. No, it would be on the end. You'd put a little string right there and hang it, and this whole thing should balance perfectly. And it turns out that it is the average of the x-coordinates and the average of the y-coordinates gives you the same thing. And that's worth remembering. Whether it's important to the standardized exam or not, I'm not sure. But in other math classes, this x bar and y bar and their significance, that's going to come up a lot. So it doesn't hurt to remember that. What about this last part here? Now that we've found that for at least one triangle, the centroid turns out to be the average of the x-coordinates, and the average of that is to say, the x-coordinate of the centroid turns out to be the average of all the x-coordinates of the vertices, and the y-coordinate of the centroid turns out to be the average of all the y-coordinates of the vertices. Well, that's true for one triangle. Now they ask us to try it with a different triangle and see if we get the same thing. Okay. And we create a new triangle just by moving this point here over to here and relabeling it as P. So these 2 points are the same. So we find a midpoint and go from there to the vertex. So we'll have to find an equation for our lines. For instance, we'll find this point and pretend that's a midpoint. And then it runs to the vertex here. Well, let's see what this midpoint would be. Minus 2 plus 4. Over 2. 2 plus 8. It's supposed to be an 8 there. Okay. And that's 2 over 2 is 1. And 10 over 2 is 5. So that's the midpoint over here. Write it in, 1, 5. Guess I can call that point C. Haven't used that letter yet. Now, we have to find one more midpoint. Yeah, what the heck, let's try this one. You get minus 2 plus 1 over 2. And 2 minus a minus 1. Pardon me, it's 2 plus a minus 1. 2 plus minus 1, taking the average of the y-coordinates. And what is this? Well, this is minus 1/2, right? And this is just 1/2. Does that make any sense? See, minus 1/2 and 1/2 would be right about there. Looks about right to me. So now we have to find an equation for the line from this midpoint to this vertex. an equation for the line from this midpoint to this vertex. Let's start with this one. We've already found, and I didn't write it in, did I? I should do that. Minus 1/2. 1/2. That's this point here. And let's call that D. Now I think we have everything we need labeled. And we could forget all this part over here right now. Maybe I should have erased it. We'll see. For the equation of this median from here to this vertex, well, first we need the slope. Rise over run. That's 8 minus 1/2 over 4 minus 1/2, which is plus 1/2, right? I went ahead and did some of the calculations because there was a lot going on. It's kind of boring to sit there and watch me do arithmetic. Remember, we had to find the intersection point of this median here and this one here. Now, the equation for this line, this point up here is the 0.48. So, we took 8 minus 1/2 for the change in the rise, and 4 plus 1/2, that's 4 minus 1/2. Get 15 over 2 over 9 over 2, that's 15 over 9. So, rise over run, 15 over 9. We put that in our slope intercept formula and get 15 over 9x plus b equals y. We know one point on the line, that would be the point up here, 4, 8. So we can substitute that in and write 4 times 15 over 9 plus b equals 8, which leads to b equals 72 over 9 minus 60 over 9. And that is 12 over 9, or 4/3. It turns out, as I do the equation, I should have just left it as 12 over 9. Outsmarted myself. I'm just going to have to convert this back to 12 over 9 eventually, but what's done is done. Now, we have our equation of the line. We found that b equals 4/3. We had our slope. So, we've got 15 over 9x plus 4/3 equals y. We have to set this equation, that's this one here, equal to the equation for this line here. Well, this line is vertical. No need to even try to compute a slope. We already know. There is no slope for a vertical line, and the equation for this line is just x equals 1. It could be, it just goes up and down here. X equals 1, and y is anything at all. So, what happens to this equation when x equals 1? At that point, y would equal 3. So, 1, 3 lies on this line, and it lies on this line. That's the intersection point right here. I don't know if I got room to write it in. I'm going to write it way out here. That is our new centroid, 1, 3. Now the question is, if we were to take the average of the x-coordinates and then the average of the y-coordinates for this new triangle here, would we get 1, 3? Well, I think that's a good question. Let's find out. Now our points are just about the same, except we've changed this one here. Or if I knew something about geometry, I could say, instead of this one here, I would say point L. That make more sense? We're going to change point L. and see if everything still works. We found our new centroid by changing L, R, this point here, to P, which is 1 minus 1. So now we just compute our average using the new point, and that's minus 2 plus 4 plus 1 over 3. And that, oops, is x bar. What do we have here? 4 minus 2 is 2, plus 1 is 3, divided by 3. Well, I'd get 1. What about y bar? Well, let's see, we get 2 plus 8 minus 1 over 3. It's 10 minus 1 is 9, divided by 3. That's 3. Uh-oh. What is our average? Our new coordinate, if we take the average of the x coordinates and the average of the y coordinates, it's 1, 3. Looks just like that, doesn't it? Well, that's because it's supposed to. And in fact, we could use variables in general terms here, and there is a way to actually prove that the average of the x coordinates and the average of the y coordinates will result in the same point as if you compute the centroid by drawing your medians and computing where they intersect. Drawing the medians works a little better if you have, if you're actually making mobiles and cutting triangles out, you're not going to have coordinates for your triangles, so finding the average x coordinate and the average y coordinate would be pretty tough. But you could draw these lines, find your centroid, and then poke a hole right there and affix that to the string. But if you're working with coordinates and you're doing things more abstractly, then x bar and y bar will work just as well. Pretty cool, huh? Well, that's it for now.